Hello everyone. All right, so today we will continue our development of the concept of mutual inductance, and we described the case last time where we have a winding coil, right, and then we have a current passing through the coil, I1, and then we have another coil, right, and then we investigated what would the voltage be at the output of that other coil, provided that the other coil is left open. Let's discuss now the most general case. The most general case is the case where we have current flowing in both coils. So let's say we have I1 and I2. Right? So we have I1 and I2, and we have V1 and V2. So we said the key concept here, and this concept really applies to both self-inductance and mutual inductance, really has to do with the fact that the current, and this is back to the basic physics. I mean, the current due to Ampere's law leads to a flux, a magnetic flux. So this is Ampere's law. Ampere's law. Magnetic flux is just a magnetic field distributed over an area, right? That's what it is. And then there's Faraday's law, where the of course linkage is just number of windings of the coil times the flux, and then Faraday's law states that the voltage is just the rate of change of the flux linkage with respect to time. So those will be the physical building blocks to get the circuit relationship for mutual inductance. Okay, so and then we said that in the case of mutual inductance, the case where the circuits, what's happening here is that there's a flux coming out of this coil, and then this flux goes back and it affects the other coil. It interacts, or it links with the other coil. So that's why we call it linkage, right? And then the rate of change of this flux is going to cause voltage and current in the other coil. Right? The basic property, the basic way to link that effect is to do what's called lumping. And that lumping goes back to introduce, it allows us to introduce the concept of inductance, right? So this lumping allows us to introduce the concept of inductance, both self and mutual, right? So we want to talk about the flux linkage, the thing that we can differentiate to get the voltage for coil 1, and the flux linkage for coil 2. The flux linkage for coil 1 is going to be, of course, dependent, right? The flux linkage for coil 1 is going to be dependent on the current passing in coil 1, of course, because the current passing in coil 1 is going to cause a magnetic field, of course, a magnetic flux. But also the current passing in coil 2 is also going to cause a magnetic flux that's going to reach coil 1, right? So the flux linkage is somehow going to be a function also of current 2. The constant of proportionality between I1 and flux linkage 1 is what's called the self-inductance. And then the constant of proportionality between I2 and flux linkage 1 is what's called the mutual inductance. It's the inductance at coil 1 due to current 2. And the sign could be positive or negative depending on the orientation of the coils, depending on how the coils are wound. So I'll discuss that in a bit, but let's assume for now that they could be positive or negative. Okay. Flux linkage at coil 2 again is going to be also a function of either I1 or I2 or both, right? How it depends on I1 is going to depend on the mutual inductance on coil 2 from coil 1, again positive or negative, dependent on how the coils are configured, and then plus L2, the self-inductance of I2, so self-inductance of coil 2. Okay, so the signs here are gonna depend on the geometrical configurations of the coil, right? So let me make a note on that. So note, sign depends on geometrical configuration of windings. That's really what determines what sign you have here, right? And the reason I don't have positive or negative for the self-inductance is because this follows the normal convention, right? For the self-inductance, you always assume that the current is going into the positive sign of the voltage across the inductor. So this is the typical sign convention. The same for a resistor. For Ohm's law, right? The current the current for a resistor relates with the voltage drop across the resistor using this sign convention. And the same for the capacitor. Right? So this is the VC, and then the current IC is going into the positive sign. Right? So that's why there is no ambiguity in the sign for the self-inductance. It's always positive based on this sign convention. However, the mutual inductance will depend on the configuration of the windings. And I want to show you what I mean by that. Right? So let me keep this equation. Okay, so we have the two windings. So I have I1, let's say, going in, and I2 going in, and then I have winding 1, and then I have winding 2. Now there are many ways those two windings could be configured. They are close to each other, right? But there are many ways they could be configured. We could have configured this winding to be clockwise or anti-clockwise. This winding could be clockwise or anti-clockwise. So okay, I could have like a configuration where I have a clockwise configuration, clockwise, anti-clockwise, 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 or anti-clockwise, clockwise. So 4 different configurations. Why does that matter? Well, it matters because let's say we're examining the flux linkage for wind at coil 1. So we're trying to find lambda 1. Right? This flux linkage is going to be due to the flux, right? But it's going to be due to 2 fluxes. It's going to be due to the flux due to I1. So let's say the configuration of the windings is such that the flux due to let me change the color. The flux due to I1 is like this. The magnetic field is in this direction. So this is flux 1, right? And this flux goes and goes into the second coil, right? But also lambda 1 is going to be a function of the flux due to I2. So let's assume that the I2 winding is configured, and let me change the color right now to red, right? Let's assume that the I2 winding is configured, the coil 2 winding, this is coil 2, is configured such that the flux coming out from coil 2 is going out in this direction. Again, I mean, if you go back to physics 2 or 1, it depends on the right hand rule, right? So this would be a configuration where the flux is coming out in this direction, and when the flux reaches coil 1, the flux due to coil 2 is opposing the flux due to coil 1. So it's always in an opposing configuration due just to the way we want coil 2, right? So that tells me that lambda 1 would be like we'll have the self-inductance term, but then because the flux from coil 2 is always opposing, that will cause a negative sign. The linkage decreases if I2 increases, because the flux coming from coil 2 is decreasing the flux that's emanating from it's in the opposite direction compared to the flux that's coming from coil 1 in this manner. So we have a subtraction effect. The fluxes cancel out. Well, the effect of flux coming from coil 2 is to cancel out the flux emanating from coil 1. So the total effect, to measure the total effect, we need to put a minus sign. We could have a totally we could imagine a different configuration where we have the two coils, and then I have flux 1. Let me go back to green. I have flux 1 going out this way, and then flux 2, if I go back to red, the coil is configured in a way, is wound in a way such that I2 is going to cause the flux to go in coil 2 like this. So if I draw it like this, the flux will be additive. The flux will be in the same direction of I1, right? So the flux due to coil 1 is going to be added to the flux due to coil 2, right? So therefore, the flux linkage is going to be L1I1 plus L12I2. This is what I mean when I say that the sign here is going to depend on the configuration, because dependent on the configuration, you either add the fluxes, the fluxes get additive, so the flux due to L1 is going to be added to the flux due to L2, similar to this configuration, or subtractive, similar to this configuration, either the fluxes will add together, combine, and it will be in the same direction, such as this configuration. So the flux from I1, coil 1 will be in the same direction as the flux from I2 or coil 2, or they will be subtractive, they will be in opposite directions. So the flux emanating from coil 1 will always be in the opposite direction from the flux coming from coil 2, just due to the configuration of the windings, how the windings are configured. One could be counterclockwise, the other could be the opposite, and so on and so forth, right? And there are only two possibilities. Either the fluxes are going to be additive, or the fluxes are going to be a negation of each other. It will be in the opposite direction. There are no other possibilities, right? And that is solely what determines the sign. Now we want this is not 1, and we want to figure out a way without appealing to geometry. I don't need to give you how the winding, in the same way I don't need to give you how the inductor is constructed in 3D or the resistor is constructed in 3D. I just give you the polarities and the wiring and the symbol. In the same manner, we need to give you a way to determine those different orientations without having to draw the windings in 3D space. Right? Otherwise, it will be, we're not doing physics, we're doing circuits. Right? The way to do that, the way to show that in a circuit diagram is through using what's called the what's called the dot convention. Right? The dot convention is gonna exactly tell you how to put in, what signs to put in those expressions. Okay, so that's one, note 1. Note 2, in electromagnetic theory, there is something called the reciprocity theorem, and this essentially leads us to the fact that L12 equals L21. The mutual inductance at coil 2 due to coil 1 equals the mutual inductance at coil 1 due to coil 2. Right? This is a basic theorem in EM theory. It tells you that, hey, it doesn't matter where you inject the current, whether I inject the current, it doesn't matter what I consider I1 to be or I2 to be, whether I inject the current from the right hand side or the left hand side, I will get the same effect, right? So you have to study EM to kind of prove the theorem, but we can take it as a fact. Another way of seeing that is true is looking at its mirror image. The mirror image of this theorem just has to do with capacitors. If I have a capacitor and I have V1 and V2, right? It doesn't matter, this is the ground and this is the ground. It doesn't matter if I swap, the value of C is not dependent on swapping V1 and V2. Whether I V1 and even if V1 and V2 change position, the value of C will remain the same. C is only dependent on the difference between the voltage, or C is only affected by the current that's passing through the capacitor is only affected by the difference between the voltages, right? So in the same manner, it doesn't matter where I1 is and I2 is. It doesn't matter from what perspective you look at the mutual inductance. The mutual inductance will be the same. So this is called the reciprocity theorem. It's an electromagnetic theorem. I think it has a circuit counterpart. I don't know if you covered it in the circuits one. I don't believe you did, right? But I don't want to go through it. We just take it as a established result that L12 is going to equal L21, and this we will call M. M is going to be equal to L12 and going to be equal to L21. Right. So using those two facts that the signs could be positive or negative, right, depending on the configuration, geometrical configuration, and the fact that L12 equals L21 equals M, mutual inductance is the same regardless of what side of the mutual inductance you look at, right? And then we're going to distill the sign change to something called the dot convention. Using those two facts, I'm going to now arrive at the circuit representation of a mutual inductance element. Okay. Oh, by the way, this is the flux linkage. So let me write that down again. So the flux linkage L1 we said is going to be L1 I1 plus minus L12, which we said at this point is M, right? L12 equals L21 equals M. I2, L2, flux linkage 2 for coil 2 is going to be, again, it's going to be plus minus M I1. It's going to depend on I1 and I2, plus L2, the self-inductance of coil 2 I2. What is the actual voltage? So let me draw this again. Right, so this is I1, I2, this is V1, V2, this is L1, L2, right? And there is a mutual inductance between them. They affect each other. So according to Faraday's law, just the voltage is just d lambda by dt, right? So this gives me the circuit equations. It's going to be L1 di1 by dt. Notice this part is similar to the inductance relationship, but then I have an extra term that represents the mutual inductance. So it's going to be M di2 by dt, and then V2 is going to be plus minus M di1 by dt plus L2 di2 by dt. Notice this part and this part are the mutual, not the mutual, the self-inductances. They give you the voltage current relationship that you would expect for an inductor, but there's always an extra term, and that extra term is the mutual inductance. That extra term represents the part of the voltage in coil 1 that is due to the current in coil 2. So there's crosstalk between them. So in coil 1, you will have some voltage, part of the voltage due to the self-inductance, but then and this is all due to current I1, the current going through the inductor, but then there's a part of the voltage that's coming from I2, and that comes in through the mutual inductance, right? And then in voltage V2, you'll have the self part due to L2, and then the mutual part due to I1. So this looks very similar to the self-inductance formula, to the inductor formula, with those extra added terms. Okay. Now let me talk about the sign conventions. The dot sign convention is going to fix the signs for us. And again, as I said, the signs vary depending on how the fluxes add or subtract. So this is the dot convention. Let's say we have two inductors that have mutual coupling between them, meaning that the field coming from this inductor affects the other inductor, right? And I have the currents I1 and I2, right? So the dot convention, and I have V1 and V2. The dot convention simply is the matter of putting dots on the two inductors. So I put a dot on this inductor and a dot on this inductor. Then I have a mutual inductance between them, right? And this is how you would see it, see mutual inductance described in a circuit diagram or in a circuit schematic. It will be shown like this, right? And the dot, what does the dot tell me? The dot tells me where is the current considered to be positive coming in. Right? That's all it tells me, and it tells me. It essentially tells me how that affects the voltage reaching the other coil. Meaning here, I consider the current going into the dot negative, right? And then the voltage appearing on the coil, I consider the positive sign to be in the direction of the same place as the dot, and the negative sign opposite to the dot. That's all this says. So let me try to give you some examples to see how you can easily interpret this. Right? It's a very precise thing. There's no ambiguity about it. So let's say I give you this diagram, and I put the dots in this manner. Right? And I say this is I1 and this is I2. What would V1 be if I want to write V1? Right? So remember, I wrote V1 here, but there's an ambiguity about the sign. How would I write V1 here using this dot convention? Well, I mean, the self-inductance is easy. The self-inductance will always follow this convention, right? Positive, negative, and I coming in, right? That's going to be positive, right? If I is going out, that will be going to be negative. So the self-inductance is easy. This is going to be L1 di1 by dt, because this follows the well-known convention that the voltage drop across the inductor, this is L1, L2, right? The current is going into the positive sign. Okay. Now, what about the mutual term? So I have here now M di2 by dt. Is this going to be positive or negative? Well, let's look at the dot convention. The current I2 is going into the dot. Okay, so that means that I2 is positive, right? And then the plus minus here match the dots. The plus is at the same place as the dot, and the minus is opposite of the dot. So this also is going to be positive. So it's going to be positive. And that's it. If the dot, instead of being here, was here, then yeah, the current is positive because it's flowing into the dot. But my plus minus configuration for V1, the polarity of V1 is opposite the polarity of the dot. So this would be negative. And that's it. That's how you do it. So let me do this again here. I'll change this to positive. Right, what about the secondary side? Well, right, so this is going to be L2, so this is V2. It's going to be L2 di2 I2 by dt, again from the normal convention for a single element, right? V2 is that way. And then there's the dependency on I1. So there is M di1 by dt. Is this positive or negative? Let's check. I1 is going into the dot, so I1 remains positive. There's no change of sign here. And then we are finding the voltage, the polarity of V2 is this. And the polarity of V2 matches the polarity of the dot on the secondary coil. So this also is positive. Right? And that's it. Let's do another example. Let's do this example. So I have a winding like this, a winding like this, I have a mutual inductance M, and now the dot is at the bottom. And my current polarities are like this, I1, I2, then I want to find V1 and V2. Okay, so this equals what? What is V1? V1 again is the self-inductance term, L1 di1 by dt. All right, and again it has M di2 by dt. That's a mutual term. That's the effect of I2 on coil 1. Right? Is this positive or negative now? We don't know until we look at the circuit and the dots and the directions of all the currents and voltages and polarities of all the voltages. So I2 is going in here, so I2 is going out. This is I2. So I2 is going outside, out of the dot, is emanating from the dot. So that means that I2 needs to be negative. So there's a negative sign here, right? We're still not done. We have to look at the polarity of V1. The polarity of V1 matches the dot, so there is no extra negative sign here, so this thing remains negative. Okay, let's look at V2. So there's again the very easy self term, right? I2 is going into the positive sign, so it becomes L2 di2 by dt. That's the self term, self-inductance term. And then we have M di1 by dt. That's the mutual term. Now, is this positive or negative? Well, let's check. Right? Let's check. Current I1 is going into the dot, right? Is going into the dot, so that means I1 is positive, remains positive, right? But we are still not done. We have to check the polarity of V2. The polarity of V2, notice, is opposite the polarity of the dot in coil 2, right? The dot is going from here to here, right? The polarity of the dot is opposite the polarity of V2. So this introduces a negative sign. So we need to put minus M di1 by dt. Right? I hope it's clear. Let's see if there are more examples in the. Right. Yeah, I mean, those are the two basic configurations. The dots, I mean, that's the only thing that could happen. Dots could either be, in the same direction. So both dots are in the same direction, or the dots could be opposite. Really, that's the only thing that could happen. Right. So I mean, I don't know. Let me do something random. Let me say, hey, this is I1. Let me do something like the most random thing ever. And let me say, hey, I1 here is I1 and I2 is leaving, right? And then I want to measure plus minus V1 here in this way. And then I want to measure plus minus V1, V2 in this way. So V2, notice, is opposite of V1, right? And then let me put the dots in a random manner. Let me put the dots like this. So, I just made up something on the spot, right? So I put the currents randomly. Instead of both the currents coming into the coils, one is coming in, one is coming out. The voltages are opposite. V1 is opposite to V2, and then the dots are opposite, right? I should still be able to completely describe the voltages using this convention. it should be completely deterministic. There should not be any questions about it, right? The technique should work all the time, should exactly give you the science. All right, let's actually, for the fun of it, let me do this. Let me show, so I1 move out, going out this way. Okay. Right, so what is the self term here? Well, again, notice, I did this, by the way, I flipped the direction of I1. I wanted to show you an example where the self-inductance term gives you a negative sign. Well, how come? Because this I1 is going in, right? And I1 is going into the negative sign. See that? So that tells me that the self-inductance term is going to be minus L1 di1 by dt. Right? And the minus sign is just because this is a case where the current is going in the opposite direction. It's not following the convention where if I have VL, the current is going in. Right? This, remember this formula from circuits 1, VL equals L di L by dt, is only correct if you're following this convention. If this is VL and if this is IL. If IL is inverted, you have a negative sign here. So you have a minus L di L by dt. Okay. So I just flipped this just to show you this effect. Okay. What about the mutual term? So I have M di2 by dt. Okay. Well, let's start. Let's look at the current. The current is leaving the dot instead of entering the dot. So that means this is a minus sign, adds a minus sign. Okay. But also, V1 has an opposite polarity to the dot at coil 1. So that introduces another minus sign. So this becomes positive. Okay. I hope you're following this. I hope it's clear. We can keep doing examples and hopefully it will be clearer. Okay. What I'm trying to say is that you do not have to appeal to the geometry of the windings. You don't have to imagine how they are configured, how they are wound. The dot convention is a circuit theory centric way of determining all those voltage and current relationships. Okay. For mutual inductance. So let's look at V2. V2 is going to have a self term, right? It's going to be L2 di2 by dt, and this is positive because I2 is going in, right? This follows the self-inductance convention. I2 is going into the positive sign, so that's fine. This is positive. And then what about the mutual term? M di1 by dt. How I1 affects coil 2. Affects the voltage at coil 2. Well, let's examine it again. I1 is going, let me write this property. I1 is going into the dot, so I1 is positive, that's fine. Right, but that's not enough. We have to check the relationship of the polarity of V2 versus the polarity of the dot at coil 2. Right, so I1 is going into the dot, so I1 remains positive, but V2 has opposite polarity to the polarity of the dot at coil 2, so this introduces a negative sign. So this is how you would write V1 and V2 in terms of the self-inductances and mutual inductances. Right, you have to follow the self-inductance sign convention and the polarity convention for the dots. All right, let's do some examples. Example. So let's right. So we have this certain configuration. So we have this wherever the circuit is. Then we have I1. And I have L1, and V1t is like this, plus minus V1t, and then I have I2t, and I have another inductor, L2, and they're mutually coupled, the coupling constant is m. Then I have plus minus V2t. Okay, so I want to express V1 and V2t for this kind of circuit. So let's do it. So V1 of t, well, I1 is going out clearly, right? So it's going out of the where the positive sign is for V1, right? So using the convention for the self-inductance, I have a minus sign, L1 di1 by dt, and then I have the mutual term, m di2 by dt, right? I2 is going out of the dot. By examining its direction, it's going out of the dot, so that indicates that the sign could be negative. So I'll put a negative sign, but I have to investigate the polarity of V1. The polarity of V1 matches the dot on the primary side, so this stays negative. Okay, V2 of t now, again I2, let's see, right? So V2 of t. So notice that I2 is coming in here. Let's start with the self-inductance. I2 is coming in, but I2 is coming into where the positive polarity is. So the self-inductance. So for the self-inductance term, you always look at the current direction and the positive polarity for the voltage. For the mutual, you look at that, but you also look at the dot. Right? So I2 is going into the positive polarity, so the self-inductance component is positive, L2 di2 by dt, and then I have the mutual part, m di1 by dt. All right, and let's examine that. I1 is leaving the dot, okay, so that's negative, but we're not done. The polarity for V2 is opposite the polarity of the dot. So we invert, we put in another minus 1 and we end up with plus. So because I1 is leaving the dot, we have a first minus sign, but also because the polarity of V2 is opposite the polarity of the dot, we have another minus sign, minus minus cancels, and we end up with plus. Okay, so this is this example. Let's do another example. Okay. So the example is to write the mesh equations for this circuit. Right, so we have this circuit, V1 of t, then I have R1, then I have L1, and then I have L2, right, and then I have R2. And I want to write the equations using KVL, of course, for those two mesh currents, I1 of t and I2 of t. The twist here is that those two inductors are coupled. We don't have to draw the two coupled inductors close together like that in the circuit. I mean, they could be close together in real life. They have to be to couple, but we could draw them farther apart. Right? So those two inductors are coupled in this manner. So there is a coupling constant M, and this is the dot configuration. All right, and we want to write the two mesh equations. So let's do that. Okay, so nothing fancy about writing the mesh equations. We just, go through the loop. So I'm starting from here. So I have minus V1 of t, right, and then plus I1 of t R1, this voltage drop. Then I need to find this voltage across the inductor L1. So this again, because of the mutual coupling, this will have a self component and a mutual component. Let's start with the self component. The self component is just going to be the regular I1, sorry, it's going to be the regular L1 di1 t over dt, right? I1 is going into the positive sign here, right? And then what about the mutual component? So there's a mutual component. So there is also an m. There's an m, and that m is going to be di2 over dt. But what's I2 in this case? I2 is the current going in this way, right? This is I2, isn't it? Right? So I'm going to use this convention. I'm going to find the current going inside the dot. So the current going into the dot is going to give me like a positive sign, right? And then the polarity here that I'm interested in for doing KVL is the same polarity as the dot on the primary side on the coil, on the primary coil, right? But the question is, what is this current going into L2? The current going into L2 is not just a single current. It's a current that you get from I2 minus I1, from subtracting the two mesh currents from each other. So the current I2, the current going through coil 2 is really I2t minus I1t, right, over dt. This is the voltage across this element. The voltage across this element, this L1, is going to be the voltage due to the self inductance, which is L1 di1 by dt, and then the voltage due to the current passing through the second coil, which I know to be I2 minus I1. And then using the sign convention, this is going into the dot, and the polarity I'm calculating for the voltage I'm interested in that I'm applying to KVL is the same polarity as the dot. So that's why I have a plus sign here. And then finally, plus I2 t R2 equals 0. I can rewrite that to get my first mesh equation. So I can rearrange the constants, right? So I have V1 of t. Let me arrange everything here. So I have, what about I1? Just I1 by itself. So I have R1 I1 of t. And then I have plus R2 I2 of t, this term, right? And then I have di1 by dt, but then I have di1 by dt, and then I have minus di1 by dt with the constants L1 and m. So I have plus L1 minus m di1 t over dt. And then, right, and then I have plus m di2t over dt equals V1 of t. This is mesh equation number 1. Okay. Now I want to do mesh equation number 2, which is this equation for this loop. Again, I follow the loop, right? So I want to start with this voltage. So I'm doing KVL and I'm moving in this direction clockwise. So I start with this voltage. So I have plus first, and then I need to add the self inductance, the self inductance component, which is now what? Which is going to be L2 d I2 minus I1 over dt, right? That's the self component. Let me put in t, I2 t minus I1 t over dt. But before I move on to R2, I have to add the mutual component, right? The mutual component is going to be m di2 by dt, right? I2 goes through the second coil, this coil here, and affects the voltage in this coil here, right? What about the sign? Well, I2 is sorry, not I2, I1, I made a mistake. Okay, now I1 is going into the dot, right? This mesh current is going to the dot, so this is positive. But what about the polarity? The polarity of the KVL voltage also matches the dot, polarity of the dot, so this remains positive, right? And now I go to R2 plus I2 R, let me put in T, I2 T, R2 equals 0. Right, and now I'm ready to rearrange to write the second mesh equation. The second mesh equation is just going to simply be, well, let me take I1 by itself. So I have di1 by dt and minus di1 by dt. So it's going to be m minus L2 di1 by dt. Right, so I took care of this term and this term. And then I'm going to have plus L2 di2t over dt plus I2t R2 equals 0. And this is mesh equation number 2 that we got by taking into account the mutual inductance. Right, so now we want, right, so this makes sense so far. So we have R1 I1, R2 yeah, actually wait a minute, oh, I made a mistake somewhere. Oh, I know what okay, yeah, so the first one is correct, this is correct, right, so this is absolutely correct, but I think I made a mistake in the first one, because in the first one I did, well, what I did is I did this external loop. That was my mistake. I should have stuck with this mesh. Okay, so I mean that's fine. Let's redo it. Yeah, that was my oversight. I did the whole big loop rather than sticking with the mesh. So that's fine. Let's redo it. Minus V1t. I'm moving here again. Plus I1t R1. And then I go here to the mutual, to this mutual inductance. So now I have the self term plus L1 di1t dt, right? But then I need to add the mutual term. So this is going to be m di2t minus I1t over dt, and then I want to determine the sign. So I2 minus I1 is going in this direction, it's going into the dot, and the voltage polarity matches the voltage polarity. This is going to be positive. And then I need to move here into this branch. What is this? Okay, so now I need to add the voltage. Okay, now the KVL voltage that I'm calculating is going to be this KVL voltage. Okay, so now I need to add first the self-inductance, which is L2 d I2 I1t minus I2t over dt. Let me erase this. This is mistaken. Right, so L2 di1t minus di2t, this is the self-inductance. And then I need to now add the mutual component, which is M. Right, so I need to I know what the current going in here is. This is I1, right? So this is the mutual current. This is I1. I1 is affecting the current here. So this is going to be di1t by dt. That's the mutual component. That's how I1 goes and affects the voltage across L2. But now we have to determine the polarity. So this makes it more interesting actually, right? So notice that I1 is going into the dot. So this is positive still. But also notice that the dot here, the KVL voltage polarity, is opposite the dot polarity. So I have a minus sign here, right? And now this equals 0. And this now I can rearrange. So I have equals V1T. And then let me arrange the things without the d by dt. So I have a single, yeah, it's only I1. So I have I1 TR1, and then di1 by dt. So I have this one, and this one. So I have plus L1 plus L2 minus M di1 t over dt. And then as far as no. So I have di1 by dt, I have L1, I have L2, I have minus M, and I have another minus M. So this is minus 2M. I have this, okay? And then I have di2 by dt. So I have this term, which is M, and then minus L2, and that's it. And that's only di2 by dt. di2 t by dt. So this is mesh equation, the correct mesh equation number 1. While this is mesh equation number 2. Yeah, sorry about that. All right, so let's do another example. Before we do the next example, so up to this point we are talking about signals in the time domain, v of t, I of t in general, right? And so the question is, can we also do AC analysis with the mutual coupling? I mean, yes, we can. I mean, all we have to do, we have to kind of redo the phasor analysis that we learned about, and it still applies. You know, the phasor analysis that we know how to do at this point, and I will remind you of it. Right now, I'll remind you of the steps we had to take to apply it. Right? So we can all still apply it to those kind of circuits. So let's say I have this circuit. Let me assume a certain configuration. So I have the dots like that. I have V1, right? V2, and then I have I1. Okay, but now at this point I'm gonna do everything as a phasor. So I have V1 because now I'm gonna assume that I have an AC voltage and an AC current flowing through the mutual inductance and the self-inductance. So everything is going to be phasor. This is I1 as a phasor and I2 as a phasor. So how do we write the mutual coupling equations with phasors? We have to remember, it's very similar to what we did with self-inductance. We have to remember what does the phasor notation means. When I write V1 as a phasor, although I'm writing it as a phasor, as a complex number, there is implicitly an EJ omega t that exists that I have dropped. Remember, that's how we derive this phasor notation. In any circuit equation, we'll always have EJ omega t terms that are on both sides, and they always cancel out, and we don't need them to solve for the phasor quantities, but they are implicitly there, although we drop them, right? Essentially, what the EJ omega t means is you know what EJ to theta means as far as a complex number. It means a rotation, right? So if you have some value, complex value, and you multiply it by Ej theta, that means you rotate that complex value by an angle of theta, right? So multiplying by Ej omega t just simply means taking that phasor and imagining that it's rotating by an angle of omega t. And given that t is time, so this is a continuously rotating arrow, essentially, right? But we don't care about rotation, right? Because everything, all the arrows are rotating at the same, with the same frequency, same omega, so we can cancel the Ej omega t and imagine that all the phasors are stationary in place. All that matters is the angle relationship between the different phasors. It doesn't matter that all of them are rotating. Okay. So what you have to remember is that there's always this implicit Ej omega t. So let's rewrite those equations with the implicit Ej omega t, right? So let's start with the time domain equations. So V1 of t equals, well, for this configuration, so we have V1 of t let's write this equation using the time domain, corresponding time domain signals. Then we will go to the phasor domain or to the AC domain, right? So so V1 of t equals what? Equals again L1 I1 of di1 of t over dt. There's the mutual part, which is m di2 of t over dt. Again, the current I2 is going into the dot, positive, and the voltage polarity matches the dot, so positive. And then V2 of t equals, let me start with the mutual term, so m di1t over dt. And again, I1 is going into the dot, so this remains positive, and the polarity V2 matches the polarity of the dot, so this remains positive. All right, plus the self-inductance term, which is L2 di2t over dt. I'm interested now in writing this in phasor form, meaning I'm assuming at this point that the voltages and the currents are all sinusoidal, right? Because they are all sinusoidal, right? I know that V1 of t equals the real part of V1 phasor Ej omega t. That's what V1 of t is, and V2 of t is the real part of the V2 phasor times Ej omega t. And so for the same for I1 of t and I2 of t, right? It's the same thing, right? So I can plug in those complex values in this equation, and then to go back to the real part, I just take the real part of those equations. That's it. I ignore the image. I mean, I can plug in this complex value in the equation, and it should still apply, right? Because the imaginary part will be the same, but with a sign instead of a cosine. So those equations should still apply. So and what this gives me, plugging the complex value back in, gives me is that I can now differentiate Ej omega t, and I then can cancel out Ej omega t again. So let me plug in the complex representation into those equations. So I end up with V1 phasor Ej omega t equals L1 d V1 phasor Ej omega t over dt plus m d sorry, not V1, I1, it's the current, I2 phasor Ej omega t over dt, and then V2 phasor Ej omega t equals m di1 Ej omega t over over dt plus L2 di2 phasor ej omega t over dt. Now I can do the differentiation easily. I can take I1 out. I can differentiate ej omega t. I end up with j omega ej omega t, right? Plus I differentiate, I take I2 out, of course. This is I1, this is I2 phasor, it's constant. And then I differentiate ej omega t. I end up with j omega ej omega t. Same thing here, g omega m I1 ej omega t, and then plus j omega L2 I2 ej omega t. As usual, the ej omega t cancels out. It's not relevant for solving the equations anymore, and we end up with those two phasor equations. So this is what the phasor equations for a mutual inductance look like. So V1 is going to be j omega. Instead of the differentiation, we have j omega. That's what it amounts to, right? So it's going to be j omega L1. This is the self impedance I1 phasor, and then we have the mutual impedance, which is j omega I2 m I1. So this is called the self impedance, and this is called the mutual impedance. So m by itself is the mutual inductance. If you have an inductance, you multiply it by j omega, you get impedance. We know that. J omega m is the mutual impedance. And then V2 equals j omega m I1 phasor plus j omega L2 I2. Right? So we will do a bunch of examples with mutual inductance and mutual impedance. That's what we will do next time. I think we are out of time at this point. Alright guys, see you next time. Thank you.